Hello students, welcome back. In this video, we are going to go through chapter 12, section 1. We are not going to do section 2. So this is analysis of variance. And we are only going to be sticking with one-way ANOVA or one-way analysis of variance. We are not going to do two-way. So the key concept here is we are going to introduce the method of one-way analysis of variance, which is going to be used to test hypotheses that three or more populations have means that are all equal. These are pretty complicated to do by hand, so we will be using technology for them. So we are dealing with F distribution, and similarly to previous chapters, the F distribution is going to be related to two degrees of freedom, one for the numerator and one for the denominator, as F is found by the standard deviation of the first sample squared divided by the standard deviation of the second variable squared. So the F distribution is not symmetric, it is skewed right. And again, the values of F cannot be negative, and the exact shape is going to be dependent by using that chart. But we're going to be using only technology right here. Okay, so I thought that we got rid of this problem. Okay, sorry about that. So one-way analysis of variance is a method of testing the equality of three or more population means by analyzing sample variances. So pretty much you have three different samples and you have the mean of each of them, and you want to test the claim that all of those three samples have the populations of those three samples have the same exact population mean. Okay? So here are the requirements, nothing much more crazy or out of the ordinary. The populations have distributions that are approximately normal. The populations have the same variance or standard deviation. The samples are simple random samples, so it's good data. They are independent of one another, that one's important. And the different samples are from populations that are all categorized in only one way. So the data is related in some extent, but they are. Let me go to the example. I really think that it'd be much easier once you see it written out in an example form. So sorry about leading you there and then leaving you hanging. So here's the procedure for testing it. We are going to be using technology to obtain the results that include the test statistic and the p-value. So same as before. We're going to identify the p-value from the display. I am going to be showing you how to do this with StatCrunch. And then all you do is you form a conclusion based on the criteria. So if the p-value is less than A, we reject the null hypothesis. If the p-value is greater than A, we fail to reject the null hypothesis. Same idea going on, just a different type of test. So, study strategy. Understand that the small p-value leads to rejection of the null hypothesis, and we want to develop an understanding of the underlying rationale by studying the examples in this section. So let's go right to an example. It's a quick, very good example. So we want to know what the relationship is between the lead content in individuals and their performance IQ. Okay, so if you have low blood lead levels, medium blood lead levels, and high blood lead levels. And we want to know, does the amount of blood lead in your body affect your IQ? So how we're going to do that by doing a one-way analysis of variance. So we are going to have a significance level of alpha is 0.05 to test the claim that the three samples come from populations with means that are all equal. So basically, if they're all equal between these three groups, then blood lead level has no impact on performance IQ. So first you have to do the requirement check, blah, blah, blah. We're all satisfied. Yay. So the null hypothesis and the alternative hypothesis are as follows. The null hypothesis is that the mean of data sample 1 is equal to the mean of data sample 2, which is equal to the mean of data sample 3. They're all equal to each other. You can't have one that's different because that would be what the alternative hypothesis is. And the alternative hypothesis states at least one of the means is different from the others. So you use technology to obtain the analysis results, and here is what you get from the different tabs. And I will show you how we do this using StatCrunch. So you type in all your data into variable 1, variable 2, and variable 3. Then you select stat, ANOVA, one way, and then under compare, select the columns, highlight all 3 variables, and hit compute. Let me just quickly show you how to do that. Oh, that's not what I wanted. Where am I? Over here. Okay. So I typed in, let me make this a little split screen. I typed in all my data values. It took a little while. It's kind of annoying. I wish they did one with fewer numbers, but here, variable 1 is going to be your low blood lead levels. Variable 2 is going to be your medium, and then variable 3 is going to be your high. Okay? So then the steps is type in all data. We did step 1 already. Then we type in, or we go stat, ANOVA. We're doing one-way analysis of variance. We're going to highlight all 3 of these, so hit shift to hit the bottom one or hit the control key, and we are going to hit compute. Now my values were very slightly different from theirs for this one. I'm not sure if maybe I typed in something wrong or if they typed something in wrong, but there were so many freaking numbers for variable 1 that you get the process, okay? I won't expect you to type in that many numbers. I just want you to know how to use StatCrunch to get the values. So let's analyze our values. So right here you see that variable 1 had 78 numbers, variable 2 had 22, variable 3 21, and then it gives you your mean of each of these. So you can see that these 2 means are very, very similar, but variable 1 has a much higher mean, which kind of makes sense. You would think that, lead is obviously poisonous, so if you have a lower lead level in your blood, that might make you smarter. So this is just kind of having the data show that. And then your ANOVA table right here is showing the degrees of freedom and your F test statistic and your p-value. So again, my numbers are very slightly different. I'm assuming maybe I just typed in 1 or 2 numbers wrong because the process was correct. And because our p-value is very low and it's lower than the significance level of alpha is 0.05, we reject the null hypothesis of equal means. So there is sufficient evidence to warrant rejection of the claim that the 3 samples come from populations with means that are equal. Okay, making this back to a single screen, and let's review that from the current slide. So to interpret that is, we cannot conclude that any particular mean is different from the others, but we can informally note that the sample mean for a low blood lead group is higher than the mean for the others. So a caution, when we conclude that there is sufficient evidence to reject the claim of equal population means, we cannot conclude from this method that any particular mean is different from the others. So what does that mean? Well, right here, this interpretation over here, that's not telling you which mean is necessarily different. Now we can just see, just by common sense, okay, this is the mean that's different, but we want to stress that the test isn't actually telling us that. That's just our ability to interpret data ourselves. So that's just a cautionary note that it's not telling you which particular mean is different from the others. It's just telling you that they are not all equal. So how is p-value related to the test statistic? Okay, larger values of the test statistic result in smaller p-values, so it's right-tailed. So if the F is here, we fail to reject. And if the F is here, which is a large F value, small p value, this was small F value, large p value. If our F is over here, we reject equality of population means. So I think this was a similar chart that we used in a previous section. So the F test statistic is going to be the variance between samples divided by the variance within samples. But again, we're not going to be worrying about calculating this by hands, but I do want you to understand generally where it's coming from. So the numerator of the F test statistic measures variation between sample means, which is why you would want them to be relatively close together. And the estimate of variance in the denominator depends only on the sample variances and is not affected by differences among the sample means. So consequently, sample means that are close in value result in small F statistics and a large p-value. So we're going to do a little mini example that's going to really show what we mean by that. So we're going to calculate the F statistic F with a very, very simple example, because we're gonna, normally it's very difficult, but because we're only using n equals 4, it's not too bad. So let's just do that. So we have, we are going to compare data set A to data set B. So these are two independent tests that we're going to be conducting, but we just want to compare the values. So data set A, we have our sample 1, sample 2, and sample 3. 7366, 6558, 4767. So n is only equal to 4 for all three of them. So then we get our n1 equals 4. The mean of those is 5.5. Standard deviation, or the variance actually, is 3, and so on. And then from here we get our variance between samples is 0.332, and the variance within the sample is 2.3333. which gives an F statistic of 0.1428. So pretty small. Now, all we did from dataset A to dataset B is we added 10 to each of the values in sample 1. So notice how sample 2 and sample 3 are the same in dataset A and dataset B. But in sample 1, we added 10 to each of these. Now we're just going to see how it affects the F statistic and the p-value. The same methodology. Ooh, look at how much larger this F value is and how much smaller the P value is. So that's just showing you the effect of the sample means. Okay, so finding the critical value. The critical value of F is found by assuming a right-tail test, because large values of F correspond to significant differences among the mean. Look back here. Large value of F, very small P value. So you know what a small p-value is. If the p is low, then null must go. So then the degrees of freedom, we know are, well, k would be the number of samples and n is sample size, so that gives you your degrees of freedom. So let's understand the effect of a mean on the F statistic. So the 3 samples in dataset A are identical to the 3 in dataset B, except in sample 1, the first dataset has 10 more in dataset B than A. So then adding 10 to each data value in the first sample of dataset A has a significant effect on the test statistic, with F changing from only 0.1428 to a whopping 51.5721. Let's show you how that came from again. It went from this small number, happy, we're happy, to this huge number, unhappy, sad. Where was I? Okay. And then the same addition of 10 results in a huge difference in the p-value, which changes from 0.866, which is very high, to a very, very small p-value. So why is it such a difference? Well, the 3 sample means in dataset A are very close. Look at how close these are. But the sample means in dataset B are not close at all. So the 3 sample variances in dataset A are identical to those in dataset B. So the variances are still 3, 2, 2, 3, 2, 2. but the sample means are what are dramatically different. So the variance between samples in dataset A is 0.3332, but for dataset B it is 120.3332. So that's indicating that the sample means in B are further apart. So the variance within the samples is 2.333 in both dataset A and B, because the variance within a sample isn't affected when we add a constant. So the change in the F statistic and the p-value is attributed only to the change in the mean, x bar 1. This illustrates the key point underlining the method of one-way analysis of variance. So the F statistic is very sensitive to sample means, even though it is obtained through two different estimates of the common population variance. Okay, so for the next few minutes, we're going to talk about informal methods for identifying which means are different. Now, I'm not going to actually test you on this, but I want you to kind of just know that this is out there. So basically, think back to our blood lead levels. We didn't know which of the samples are different from the other. We just know that all three of them are not equal. So after conducting an analysis of variance, we might conclude that there is sufficient evidence to reject a claim of equal population means, but we cannot conclude from this method that any particular mean are different from the others. So here are just two informal methods. You can construct box plots of the different samples and examine any overlap to see if one or more of the box plots is very different from the others. You can also construct a confidence interval estimate of the means for each of the different samples, then compare those confidence intervals to see if one or more of them does not overlap with the others. So you want to just see where the overlap is, and you can do that from either of these. Again, I'm not going to ask you to do that, but I want you to just know that it exists. So those are the informal methods in the previous slide. Here are the formal methods. So you could do a range test, allows us to identify subsets of means that are not significantly different from the other. And then multiple comparison tests uses pairs of means, and they make adjustments to overcome the problem of having a significance level that increases as the number of individual tests increases. So here is just what we mean by the multiple comparison test over here. So we are going to do a separate t-test for each pair of samples. So each pair of samples, so 1, 2, 2, 3, 1, 3. But then make adjustments described in the following steps. For an estimate of the variance, we use the value of MS, the error, which uses all the available sample data. That was shown on the other slide in my conclusion. So we have our t statistic is the mean of sample 1 minus mean of sample 2 divided by the square root of the error multiplied by 1 over n1 plus 1 over n2. So after calculating the value of the test statistic for any particular pair of samples, we can find the critical value t or the p-value, but make the following adjustments so that the overall significance level does not increase. So for the p-value, we use the test statistic t with degrees of freedom n minus k, where n is the total number of sample values and k is the number of samples. And then we find the p-value using technology or table A3 and adjust the p-value by multiplying it by the number of different possible pairings of two samples. And then the critical value, we find the critical value. When finding the critical value, adjust the significance level A by dividing it by the number of different possible pairings of two samples. So let's look at an example of that. We'll go through this quickly. In the first example, we conclude that there is sufficient evidence to warrant rejection of the claim of equal means. Let's use this test. I don't know how you pronounce that. Bonferroni, sure. So we use that with a significance level of 0.05 to identify which mean is different from the others, even though we kind of know what it is. So we require separate t-tests for each possible pair of samples. So there are 3 possible pairs of samples, 1, 1, or 1 equals 2, 1 equals 3, and 2 equals 3. So let's begin with the first one, that the u1 or mu1 is equal to mu2. and then use the sample data given. And this is the same example with the blood levels. Okay, so we have N1 equals 78, and the mean is 102.7, and then N2 is 22, and then the mean is 94.13. So technology shows us the results have a MS error of 248.424127. Plug that in, we get a t statistic of 2.252. This is just the equation we had on the previous slides a couple ago. The degrees of freedom is going to be 118. So with a test statistic of t equals 2.252 and degrees of freedom of 118, the two-tailed p-value is 0.026, but we adjust this p-value by multiplying it by 3, which is the number of different possible pairs. Remember, we had these are the 3 different pairs over here, to get a final p-value of 0.0785, or basically 0.079 when rounded. Because this p-value is not small, less than 0.05, we fail to reject the null hypothesis. So it appears that samples 1 and 2 do not have significantly different means. So instead of continuing with separate hypothesis tests for the other 2 pairings, this display below shows all the Bonferroni tests, and then in this results, low lead levels are represented by 1, medium 2, and high 3. That's shown over here. So although the analysis of variance test tells us that at least one of the means is different from the others, the Bonferroni test displays do not identify any one particular sample mean that is significantly different from the others.